Hi dear students, this is the last part of our last chapter, chapter number 6. It is Solubility Equilibria. Okay, first let's talk about a little bit dissolving and precipitation process. Now remember what was dissolving. If you have a polar solute, it can dissolve in polar solvent. If you have a nonpolar solute, it can dissolve in nonpolar solvent. So we have that rule, like dissolve in like. But some salts dissolve in water very little, so you have that solubility equilibria for those salts. Solubility of salts and precipitation conditions. Solubility equilibrium in salt solutions is obtained when rate of dissolution or rate of dissolving becomes equal to rate of precipitation. Now remember, when we're talking about chemical equilibrium, this is a kind of a physical equilibrium in fact. In chemical equilibrium, we define it as the rate of forward reaction is equal to rate of reverse reaction. In this case, we just change the names. We tell them as rate of dissolving becoming equal to rate of precipitation. For example, you're given zinc hydroxide here. If you like to write its solubility equilibria, it is going to be like this. So this is going to be zinc 2 plus in its aqueous form plus 2 hydroxides minus 1. And you can calculate KSP here. KSP is used only for the salts that are slightly soluble in water. So what is the meaning of KSP? This is solubility product. Again, in fact, this is an equilibrium constant, but in an equilibrium constant for a physical change, again, the same things are valid. What were these things? You were not taking the solids and the liquids, you are taking only the aqueous and gas forms. But in this topic, you're going to only have the aqueous forms because it's about dissolving in water. Now, what about the graphics? Rate versus time. For a while, the rate of dissolving is going to be higher than rate of precipitation. Then rate of precipitation is going to be equal to rate of dissolving. So this is rate of dissolving. This is rate of precipitation. Remember, we have drawn the same graphic in the previous videos. Now, what about the molarities? For example, if you just dissolve here, that one, when you dissolve 1 molar of zinc hydroxide in water, this means that it produces 1 molar of zinc 2 plus and 2 molar of hydroxide minus 1. So when you draw the graphics, it's going to be like this. You have zinc 2 plus here with a molarity of 1. And what about the hydroxide? It's going to be double of it. And you're going to have 2 molar of hydroxide. So you can be given a graphic, and by looking at that graphic, you can just take the formula from it. So if there is dissolving process, this means that there is also the precipitation process. To check whether there will be a precipitation or not, reaction quotient is calculated. Now, did you remember the reaction quotient? You were just calculating as the K, that equilibrium constant. You were just taking the products and over reactants, and you were just comparing with the KSP K values, equilibrium constant values. So we're going to do the same thing here, but only the words that we use are going to be changed. For example, if QSP, the QSP at that moment is higher than the KSP, the reaction will favor reactant side, meaning there is precipitation. If QSP and KSP they are equal, so this means that the reaction is at equilibrium, meaning you have a saturated solution. And if QSP is smaller than KSP, in this case, the reaction will favor product side, meaning there is an unsaturated solution. So This favor can occur if and only if there is a solid in the container. If there is no solid form of the solute, this means that the change cannot favor the product side. So please be careful with the questions. Okay, the factors that affect solubility. First one, the common ion effect. In fact, we just defined the meaning of solubility. Solubility was the amount of solute that can be dissolved in 100 grams of water. And temperature can change this value, sometimes pressure can change this value, but in this chapter common ion effect is really important. Now how can I just tell you that? For example, you have a pure water in a container, you have another container and it has potassium chloride aqueous solution, meaning there is potassium chloride solid plus the water molecule. Now you add both of them sodium chloride, let's say. Now which one do you think will dissolve sodium chloride more? Let's say that this is solubility 1, this is solubility 2. Now when you look at the first container, that one, there is no common ion with the solute that you are given. There is no sodium plus 1 here, no chloride minus 1 here. So you directly put sodium chloride into the solution. But when you look at that one, you have common ions, meaning you have coming some chlorine minus 1 here and you have another chlorine minus 1 here. So this means that the solubility of sodium chloride is going to be really lowered. So solubility in the first container is going to be higher than solubility in the second container. And the temperature. If the dissolving process is endothermic, the solubility of the salt increases as the temperature increases. So what kind of graphics you have? So if you have a solubility to temperature graphic, it was going to be like this. Now what about vice versa? If the dissolving process is exothermic, the solubility of salt increases as the temperature decreases. So in this case, you're going to have a graphic just like this indirect ratio graphic. What about the effect of pH? Now I'm going to explain this effect by the help of a question. How will the solubility of magnesium hydroxide solid be affected if it is dissolved in an acidic aqueous solution, not pure water? Now let's say that this is the equilibrium of magnesium hydroxide in water. Now do you remember the Le Chatelier principles? Le Chatelier principle says if you just disturb a reaction at equilibrium, it is going to give you a response here. So if you put some acid into this solution, acid means that you have hydrogen plus ones, and those hydrogen plus ones immediately react with this hydroxide minus 1 to form water molecule. So what happens? The amount of hydroxide decreases, so the reaction favors right hand side. So this is a kind of increase in solubility and a vice versa effect with the common ion effect. So when you decrease the amount of hydroxide by putting an acid into the media, the reaction favors right hand side. This means increase in the solubility. What about the solubility of gases and pressure? Now remember, the atmospheric pressure does not have any effect on the solubility of the solids and the liquids, but the partial pressure of a gas have effect on the solubility of that gas. As the pressure of the gas, which is on the top of the liquid in a closed container, increases, the solubility of gas increases also. So this is how you drink Coke, how they make Coke. This relation was shown by English chemist William Henry by using Henry's constant. And it is known as Henry's law. In this relation, the molarity of the dissolved gas is directly proportional to the pressure of the gas on the top of the liquid. And it is this formula: solubility of that gas is equal to Henry's constant times partial pressure of that gas. So here is a constant So when the partial pressure of that gas increases, solubility of the gas in that liquid increases also. And this is the final part, formation and decomposition of equilibrium of complex. First, we have to define the coordinate covalent bond. We're going to talk about this bond a year later more. When a covalent bond is produced from two electrons coming from the same atom, it is called coordinate covalent bond, and the compound is called coordinate compound or complex. And this is explained in terms of Lewis acid-base pairs. Now remember, we have defined three different acid-base theories, and one of them was Lewis acid-base theory, and this formation of complexes is based on this theory. And how? For example, here is the ammonia. This is the dot structure of ammonia, and you have bore 3 hydride. Now, as you see, bore is a semi-metal, and it cannot complete its number of valence electrons to 8. So it can just share these 2 electrons with the bore here, and here is the formation of coordinate covalent compound. So in normal covalent compounds, 2 electrons are coming from different atoms, 1 nitrogen, 1 bore, or 1 carbon, 1 carbon, so there is electron sharing. In this case, again, there is electron sharing, but this bond's electrons are coming only from nitrogen, but not bore. So what can be given example for a complex? For example, the complex formed between the copper 2 plus and ammonia, and it is shown like this. Copper, you have 4 ammonia molecules and with a charge of 2 plus. So what kind of terms do we have here? You have copper as the central atom. Copper is the central atom. Ammonia is the ligand. And all of these bonds are coordinate covalent bonds. Stability of complexes and their formation constants. Now, why do we have this topic in this chapter? Because complexes have a kind of KSP values. In this case, it is called as formation constant. And when this formation constant, the value of formation constant increases, the stability of the complex increases also. For example, first one, you have 1 lead 2 plus here and 4 iodine. So this means that your complex contains 4 iodine atoms with a charge of 2 minus here. Why 2 minus? You have minus 4 coming from here and 2 plus coming from here. When you sum them up, you're going to end up with 2 minus. And the Kf means, again, products over reactants, which is over okay. What about next one? This copper with 4 ammonia and with a charge of 2 plus. And the formation constant for it can be written as now we said that if the formation constant is higher than the other one, that means that complex is going to be more stable. So as the Kf value gets bigger, the stability of the complex increases. So this means that second complex which contains copper 2 plus, second complex is more stable than first complex. And finally, effect of complexes on solubility. If some amount of potassium iodide is added to lead-2 nitrate, precipitation reaction occurs. Here is my precipitation reaction. This means that lead-2 iodide will have a solubility equilibrium like this. It is going to produce lead-2 plus N2 iodine. So you have a precipitation reaction, and after that there's going to be a solubility equilibrium. Now this is important, if very high amount of potassium iodide is added to lead nitrate solution, following reactions takes place also. You have lead-2 plus here, it combines with 4 iodine minus 1 and it forms that lead-4 iodide complex. So this is important. To form this complex, more potassium iodide will be needed, so the solubility of lead-2 iodide will increase.